Welcome to APA's weekly webinar. My name is Billy Zydick, Manager of Special Projects for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted to the APA webpage later this afternoon. You'll receive a follow-up email in the next couple of days with a link to the webpage where all webinar recordings are housed, as well as a link to our upcoming webinars. We have webinars planned out through the end of 2021, and they are open for registration. Professional continuing education and AIA CLU credits are being offered for today's program. And if you are an AIA professional requiring a certificate, please send an email to me at Billie, B-I-L-L-I-E, @apa.org, along with your AIA member number if you have not done so in the past. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by one of our presenters. If you are just calling in, make sure you send me an email at billie@apa.org to let me know so I can send your certificate if you requested one. The system only recognizes you if you log in. Before we dive in, let's get to know our speakers. Hailing from our Marlton, New Jersey office, Tony is part of Gannett Fleming's Engineering Technology Group, while Bill Curran is part of the firm's building business line. This team is a great example of how Gannett Fleming pairs the best expertise together to bring value to our clients. Tony Conchato is a lifelong snowboarder, fur dad of 2 rescue pups, loves cooking, gardening, and anything outside. As Engineering Technology Manager at Gannett Fleming, he supports clients and teams across a wide range of industries to implement technology best practices. In his role, he provides leadership, vision, collaboration, and vision in identifying, analyzing, and developing technology trends and processes. During the heart of the COVID-19 crisis, he actively guided project teams and organizations on the transition to remote working conditions and utilizing advanced technology to support virtual work throughout the project lifecycle. A mechanical department manager at Gannett Fleming, Bill provides design, planning, and coordination for client projects at educational, transportation, and commercial industrial facilities. As an active partner with Rutgers University and organizations such as the New Jersey Turnpike Authority, Bill works with client and project teams to implement virtual strategies to keep projects on schedule, including virtual pre- and post-bid walkthroughs. Bill is a horror movie buff and does not discriminate between the good and bad ones. Halloween is his favorite holiday, and to the extent he even has zombie figurines adorning his office. At this time, it's my pleasure to turn this over to Bill and Tony. Gentlemen, take it away.
Thanks, Billy. We have a great program in store for today as we explore the role of reality capture throughout the project lifecycle. You know, construction projects live on throughout the pandemic. The ability to communicate essential project requirements effectively while minimizing in-person interactions during pre-bid and post-bid activities is critical to the health, safety, and welfare of the entire team and those on campus. We'll share firsthand experiences with this technology that provide the safe execution of virtual pre-bid and post-bid activities in a college or university setting. This past year has demonstrated the need for new protocols and game-changing technologies. This session promotes the continuity of business, research, and educational programs associated with campus facility improvements. So here's our objectives today. We're going to understand how to assess the viability and costs associated with virtual site visits and walkthroughs, and how they can promote good health, increase safety, and improve participants' welfare. Learn from case studies about how this technology supported COVID-19 resilience and recovery efforts while enabling business continuity. We're going to explore the range of technology options that can support virtual site visits, including 360-degree photos and videos, LiDAR scanners, point clouds, BIM models, and drones. We're going to learn the value of implementing a web-based 360-degree photo viewer, or 3D model viewer that allow project teams, clients, and contractors to interactively navigate a 360-degree visual twin model to assess the scope of work and increase design accuracy and collaboration. So let's discover what reality capture is. Reality capture is a hardware and software solution that allows you to create 3D point cloud models or 3D meshes from laser scans and photographs, which translates to a virtual 3D model of your project or scope of work. Point clouds are made up of billions of 3D points that a LiDAR scanner captures, and 3D meshes are made from overlapping photos that a digital camera captures. After your model is created, you can virtually revisit your project anytime. And just think about the value that could bring to your design and construction teams. We use this data for all types of analysis, for example, measuring distance, area and volume, floor flatness and levelness, wall, floor, pipe slope, surface elevations, and more. You can also use this data for feature extraction, which is automatically or semi-automatically extracting usable 3D geometry or 2D lines from point cloud models to jumpstart your design. For example, you could extract walls, floors, duct, pipe, conduit, structural components, ground topographic surfaces, lane, curb, and rail lines, etc. Then consume that data in your design authoring tools. These 3D models and meshes can also be linked into BIM, CAD, and GIS software, such as Revit, AutoCAD, Civil 3D, InfraWorks, Navisworks, Bentley applications, ArcGIS, and more, then used to generate highly accurate BIM and CAD as-built models. You can utilize this data for all phases of a project lifecycle, including existing conditions, concept design, design development, construction, handover, and commissioning. So I want to review some examples of industry standard reality capture equipment, many of which we utilize here again at Fleming. The first category we'll look at is static LiDAR terrestrial land-based scanners, meaning you initiate a scan, reposition the scanner, complete the scan, and so forth. And this category of scanners produce highly accurate and dense point cloud models by stitching together scans that can also be geolocated. There are a wide range of costs, starting at around $15,000 for economical scanners, upwards of costs of $100,000 for high quality scanners. They average 2 to 8 millimeter accuracy, depending on scanner models, settings, and overlap between scans, and could typically take 1 to 6 minutes per scan, depending on density, picture quality, and hardware you're using. The next category we'll look at is SLAM LiDAR scanners. This technology allows you to scan as you move, so you're not stopping for each setup. They're medium density, least accurate point cloud models, but there's a lot of value related to the speed these scanners operate. Contractors are using this technology to perform construction walks, manual or even automated with robots and drones. Software can automatically identify and flag progress changes between scans. And there are a wide range of costs, starting at around $30,000 for economical scanners, upwards of costs of $100,000 for high quality scanners. And this is actually the same technology used in autonomous vehicles and the new iPhone 12 Pro, which has a SLAM LiDAR scanner built into it. They average 6 to 30 millimeter accuracy, depending on scanner model and settings. And it's the newest technology available, but it's rapidly evolving. We expect to see continued advancement with this technology moving forward. The third category we'll review is photogrammetry, which generates 3D models by overlapping photos from a digital camera, either handheld or mounted on a drone. And in other words, it's the science of taking measurements from photos. The benefit of this approach is you can cover larger areas quicker, but with a little less accuracy. The flight of drones may operate with various degrees of autonomy, either under remote control by a human operator, or fully or semi-automated by onboard computers, meaning you can pre-program flights. Alongside generating 3D models, drones can capture high-resolution 360-degree photos, normal high-res photos, and videos. Starting costs at around $3,000 to $15,000 for drones with high-res cameras, and around $65,000 to $80,000 for drones with LiDAR scanners. And finally, the last category we'll review is 360-degree photo and video. And technically, this really isn't considered reality capture, but it has a ton of value. The key features are, in comparison to the others that we just discussed, it's inexpensive hardware and extremely easy to use. 360-degree cameras capture scenes and environments in a way that no normal cameras can match. They can be handheld, mounted on a pole, tripod, vehicle, helmet, drone, virtually anything. Cost average at about $350 to $1,000 for good high-quality cameras. They're also commonly used in action sports. And it's a fast data capture process. Photos take a split second to take. And depending on the software, you can automate or manually map photos and videos to plans, which can even be geolocated. And we'll cover that integration to the project workflow later on. So how is this technology changing the way we work? And how can this help you in the current and post-pandemic climate? Not just our industry, the entire world has experienced a massive shift to the cloud with the need for easy access to data anytime, anywhere, any device. We're utilizing this technology for almost all aspects of design, using different applications to work and collaborate in various cloud platforms. Along with this shift, the AEC industry is experiencing a transition towards a common data environment, meaning regardless of the location, tool, or file format, design and construction teams collaborate on project data within the same unified platforms, using various applications, tools, and processes. There's so much value with all stakeholders in a project being able to access and utilize the I in BIM, which is information that we're inputting into our designs. To summarize, there's endless value by utilizing reality capture and BIM workflows for your designs. We're using this technology for more comprehensive project capture to build smarter designs and solve challenges during design, not construction, which is resulting in a more coordinated and efficient design, construction, and turnover process. So now that we saw examples of what reality capture is and the equipment we use to capture it, I want to take a closer look at these different data outputs and how we can share it in the cloud. So to enhance access to LiDAR data, how could your team leverage the cloud for projects, O&M, or as an internal database? A solution like Cintu allows you to interact with point cloud models with user-friendly controls and no software required. You can access your projects via a project explorer or map view, browse all scans or other data inside a project. We can set full role and permission controls, including read, write, download, and upload. You could easily share links to other parties with or without expiration dates and permissions already set. You can organize your point cloud in the work zones, which simply means grouping scans for quick and recurring access to specific areas. This is by level, which is typical, and you can quickly jump into each work zone from there. Here's an example of a point cloud organized into work zones via floor level and area. And notice the notes and dimensions available. We can jump right into a crop view that someone had saved with certain settings set. And from here, we can jump into a scan setup and switch the way points are displayed very easily. We can switch from the surface view to a panoramic photo that was captured during the scan. You can also dimension and annotate in any display mode and save those dimensions. You could easily create and save cropped areas of the point cloud, create annotations, dimensions, upload other supporting documents, and download point cloud models. You can upload photos, videos, PDFs, other images, etc. Measuring is one of the most common tools used when interacting with reality capture data, and Cintu has a really nice measurement tool where you can pin one side of your measurement, quickly measure anything off that object. And Cintu is built from a collaborative mindset. So again, all of these crops, annotations, markups, edits, uploads that you make are saved and available to the entire project team. You can run visual analysis and BIM point cloud model comparisons to confirm accuracy. And there are other products and processes available to share reality capture data that we utilize as well. But Sintu's been a great tool and process improvement for all stakeholders involved so far due to its user-friendly controls and ease of sharing and integration with other apps. So next up is photogrammetry, which could be the output from a drone or handheld camera. We're viewing a web-based solution, but this could also be utilized with installed software with more tools available for analyses and feature extractions. We can easily take measurements and notes with a solution like this. In other apps, we could combine LiDAR data with these 3D meshes and also convert these 3D meshes to point cloud models to complete feature extractions, and also link these into various design authoring applications, very similar to LiDAR for as-built modeling and more. So here's an example of a high-resolution 360-degree camera mounted on a drone. Just like sharing LiDAR and photogrammetry models, this data can be shared via secure web access in the cloud, with no software or hardware required. These high-res cameras mounted on drones capture an enormous field of view and detail from hundreds of feet in the air. You can navigate the key plan in the lower left-hand corner, which tracks your viewing perspective, or by selecting photos in the lower ribbon. And depending on the team's goals and objectives, we develop various deliverables with this drone and photo video data. We could integrate 360 photos and a sitemap viewer like we're seeing here. We could set up a video inspection with sitemaps. Video and high-res photo inspections broken into zones or sections depending on what you're capturing, or all of the above and more. And being able to easily document a scope of work with this level of detail and ease of use, then share it with all project stakeholders in this capacity, just like LiDAR and photogrammetry, it's been invaluable to our project teams and is enhancing the quality of our projects and designs. So alongside interfacing with reality capture data, as we just reviewed, we're also consuming this data in various design authoring tools for feature extraction and true as-built modeling. Here are a few screenshots during the scan to bin process, where design teams utilize point cloud models linked into Revit to generate their design models. This process can be scalable to aid in developing 3D models of any size or shape or project type. And a workflow like this becomes super invaluable when we don't have any existing plans to start our design models with. We'll typically go in, scan whatever we're capturing, and create our models from there. So let's bring this home. This slide may seem busy, but this technology has a lot of moving pieces. Like most things, reality capture can be broken down to people, process, technology. It's not just about all the cool things we can do with it. We need skilled, motivated subject matter experts to take ownership, drive change within your organization, evaluate new enhancements and inventive solutions, and be those experts other teams can rely on for projects and proposals. We need processes to effectively train various level employees on the myriad of technologies available, how it can help their teams, and what they can do with this technology. And finally, continue to develop new workflows, processes, and standards to enhance efficient, effective use of reality capture on projects. And now we get to technology. There are so many hardware and software solutions that we utilize currently, and way more that exist. It's not just the reality capture hardware. It's the high-end PCs processing this data, servers and external drives storing data, using cloud services to store and share data various ways, using different software solutions to consume data effectively and process data various ways depending on how you're utilizing reality capture. Now that we have a good understanding of what reality capture is, I'm going to hand this off to Bill, who's going to review how it's applied to all phases of design and construction.
Thank you, Tony. So as Tony mentioned, I'm going to expand on the application of this technology through the multiple milestones within a design, bid, build project lifecycle. We're going to see examples used by the team for our team internally, as well as with collaboration with our clients to help maintain the continuity of our business, regardless of what restrictions we face. So Tony covered a lot, and these examples going forward are going to primarily focus on what's shown here. To the left is true reality capture. This is that static LiDAR technology, which we set up the scan, we capture the scan, move the scan, and continue on. The other is the 360-degree photo viewer. We assess this technology to use on different projects based on what the scope is, what information is available. Obviously, there's costs and availability of equipment to consider with both technologies, where the technology to the right, the 360-degree photo viewer, is fairly inexpensive, and we have that throughout the company in various groups, various offices, multiple in certain offices. And a static LiDAR, where we have some that is a shared resource within the company and is applied, appropriately for certain projects. So going forward, before I get to the examples, I want to touch on the fact that, this captures a lot of information. But what happens when certain things are confidential? We have many clients where we sign non-disclosure agreements and have confidentiality concerns. So what to do then? With anything, it all comes down to proper planning. But where that planning, there are gaps, or we capture things that we don't want to show or cannot show, we can edit them. So the teams go to evaluate where the scans or pictures are taken, and in the field, if possible, they'll install screening. A screen is shown there to the left. We've even used tarps, sheets. It can be to any degree. But again, if it's captured, it can also be edited out to make sure we abide by that agreement. So starting with proposals, what do you do before the project's on the books and during that pursuit stage? We're going to go through how we can leverage this technology to improve on proposals and information exchange with the client. So starting here is a rendering that was developed, and it was assisted with a LiDAR scan, and it shows the final proposed product. The background for this building was constructed in two parts. You'll see covered over to the right there. To the left was what is existing and what was captured with LiDAR, as well as to the right, what was being demolished. And we had to capture this information accurately to reflect where that handshake was and give the client a very clear understanding of what the ultimate project would entail. So going into next, the LiDAR scan. So here's the scan, and this is the output viewed within Cinto. The division line between these two pieces is going to show where that mouse is drawing down, shows the existing to the right, that part being demolished, and the existing to remain to the left. These scans help get an accurate picture of the tie-in points and the dimensions of the existing structure. We traveled around the building to capture all this information, noting during a proposal phase, the planning was important. The planning of those scans and leverage the time spent and the information necessary for that. You can denote and change the model features to help capture and understand the elements that were scanned and see within that point cloud. So this, you'll see the picture-in-picture view in the bottom right shows the scans. You'll see these are large and widely spaced around. And that's on purpose because at a proposal phase, you weigh what information you need. not to shortchange it, but the amount of time spent, that project's not one. So you have to weigh that with the decision process. And to the left there, that's the demolished part. And it's important that we capture that information. And you'll see we jump between scans because this building was constructed in 2 phases, where the newer construction to the right was about 15 years later. However, not all utilities were independent. There was only one main gas service. It came in the back location of the original construction and actually divided into 3 pieces. One went off to an adjacent structure, one went to the original construction, and finally the third traveled through the original construction and ultimately to that construction that was 15 years later. The problem with this is we were demolishing the original construction. And this LiDAR helped us get accurate information of that gas line and the path of that gas line through the structure to make sure that that handshake was as seamless as possible. So going forward, we'll see the other proposals and pictures and rendering that were done with this project. So here is a rendering. This is to the front view. Again, almost mid-picture is that handshake of the existing structure, which was phase 2 of construction, about 15 years after the original construction that's going to be demolished. And the next rendering is a slightly different perspective. Now we're going around to this is all existing to remain. And finally, to the last. So let's move into design. Within design, who benefits most from these technologies and their implementation? From our perspective, it's the design team and the client. For design, it captures more accurate survey information with fewer people and in less time. The information helps construct a virtual representation of the project for continued assessment well after the project team leaves the site. As for items that are designed, we can also do a virtual clash detection and interference checks in 3-dimensional space before construction occurs. Now for the client, it also limits disruption. It limits the personnel on site and visually helps relay design approach and intent. Now, if a new project personnel on the client side is added, they can get up to speed quickly because we can understand the site conditions without physically walking and visiting it again together. It enhances facilities personnel interaction and engagement to identify exact tie-ins with a visual support representation to ensure all project team members are aligned. So this is a church that was done in New York City. This project had no existing as-built drawings. This was done with 158 scans over 2 days for approximately 33,000 square feet of scanning. And it was a complete scan to BIM process. This architectural team linked the point cloud into Revit and modeled the entire structure based on that point cloud. So let's navigate the scan. We'll first make all scan locations visible. By utilizing the 360-degree image capturing during the scan, right away, we see drainage along the building face that's resulted in efflorescence of minerals on the surface of the brick. This architectural team scanned and surveyed the facility, then linked the point cloud into Revit, and from there they modeled the entire structure, which included the church and the attached rectory. The scope of this project involved modifications to the rectory with the space, with an adjoining space that could house nearly 20 people and provide offices for each member of the mission. To do this, the facility needed to add an elevator and new ramp to comply with ADA. Lastly, envelope items were addressed, which included repointing the existing facades. Regardless of the software you're using, icons for each scan location are shown allowing you to easily navigate through the point cloud while giving proper perspective of where the scan occurred. Sorry, my light went off. This video will navigate from the large congregation areas, as you see here, into the back of house and support areas to understand the complexity of this facility, which the upper floors were in various stages of demolition and reconstruction form. Now, within the back of house areas, we're faced with small compact rooms. Here, you'll see the density of those scans shown by all the dots. We had to get within each space to allow the line of sight and get appropriate information for the LiDAR scanning. Now, this project, our client was a congregational staff, a staff that expressed concern about visualizing the whole picture. So to help navigate it, we showed the visual twin of the building. We were able to step outside the building and start to slice it up. We showed the levels, jumped to a level, and explained the process and the work happening within each space. Further detailing of site dimensions, annotation, as Tony pointed out earlier, can be put within the model and shared to help that collaborative discussion that occurs. So stepping further outside the building, you see all the information that was captured. So here's another example. This project was a boiler replacement in a central mechanical room. However, we had to capture more information than just that room. Here's an unedited scan. And the reason I'm saying unedited, you'll see off to the side some of those points that are outside the building envelope. Now, this is a line of sight technology. And with that line of sight technology, if you have a window or a transparent surface, it will go through, which can be edited later, but you'll see points that are outside your envelope. Now, this scan will navigate through all of the spaces, and off to the side are those points that were captured outside. Now, we navigate through each space, and what was captured here is to get a background. The reason to get the background outside of just the space involved is because code requires carbon monoxide detectors. And this client didn't have that background. To do this by hand would have taken an exhaustive effort, where we're able to do it with scans. We walk through the space, appropriately space the scanner to get the accurate information of the outline and necessary background at play to get all the information in a streamlined and effective process. So from there, the end product, we navigate into the scan, and here's in that hallway. Now you'll see that window was showing where points were exterior to the building. Again, with the unedited model. You can jump point to point. Here, you'll see the orbs with the camera icon, and see, as we walk through, you'll see the density changes. For the architectural, it wasn't a higher density, but when we jump into the mechanical room, it's a much tighter density. Now, this is a congested space. Scans were taken at different elevations, high and low, around equipment to make sure that we have the line of sight information necessary to help facilitate design. And with that design, we share information amongst the design team. Here, a dimension was noted, and within that dimension, there were annotations. The annotations informing them that there's currently a code violation. Improve and increase the clearance to the electrical panel. This is a clear information that is shared amongst the project team to make sure those design elements and necessary things are shared amongst the people that were on site, as well as the other support people that are helping with the project. Again, the scans here are high. This is above the pipe rack to get all that information that is necessary, and as well, jumping down low, getting under that piping, the line of sight, and behind equipment, and even between equipment. with this latest scan between both boilers. So we'll move from here into what the design end product look like. So from that 3D LiDAR scan and information, we developed the model and all the information. We also can then do our Revit work on top of that, removing the equipment that is to be removed and doing a 3D representation of all the information that then is going back into the space. With this, as well as the next slide that showed the equipment and the associated piping and all the pertinent information. So taking it from design into bidding. Why do you do a walkthrough? We see it as limiting risk. Contractor walkthroughs allow them to see the site conditions, plan their approach to the projects, and understand the obstacles. In short, they can formulate their thoughts. But in the current stage, how are these problematic? They're scheduling. They're scheduling with project managers, facility personnel, users, contractors, etc. But even after it's scheduled, there's also logistics with that site walk. You're managing a large group of people. And finally, when bidding occurs, you want to make sure there's no competitive advantage. During a normal site walk, there is talk, there's chatter, and potentially a question is asked and may be answered where it wasn't supposed to be. And now a contractor has an advantage. By doing it virtually, everyone is in the same room, can walk through the same information, and questions can be clear, concise, and everyone can be informed of the answers. So we're going to have two case studies of the virtual bidding. We'll have one with 3D photos and then a second with reality capture, where, here's a quote for one of our clients where this helped facilitate in the pandemic to maintain operations. So with the 360 camera, here's one example. It's a split screen where the picture's on the left and the plan is on the right. This shows the location where each picture was taken and the associated picture that they can pan and zoom and navigate through it. The next example is a 360 with the similar picture-in-picture, just in a smaller corner. That shows where the picture is done, but we also included the perspective, where our line of sight view is. Now, the key plan allows you to jump point to point, and this entire process was to mimic that contractor walkthrough. It is to mimic the old traditional approach of gathering that large group of contractors with clipboards in hand, walking through your site, but without the physical site presence and the logistics. Not only did the solution come from needing to support virtual walkthroughs, it came from the need to more effectively share this data with the project team. So this video, you'll see the key plan and icons, and we can jump to the different staging points as well as between different levels. Initially, we're on the ground floor, and through the side drop-down menu, we jumped up to the roof. All these examples are going to show you today is the project team, their survey was very planned out. It was planned out to avoid blind spots, allowing full view of site elements and equipment. Regardless of technology, the items that we're showing you here include line of sight information. The locations are selected, and for this, they correlate to the plan in the picture to give that perspective. This allowed the contractors and their subcontractors to understand the site in parallel with the contract documents to aid in getting informed bids. As I noted earlier, planning is very important. So we'll continue to navigate level by level and panning and zooming between the pictures. You can move to the next space and the picture can also be adjusted in size. Here in an electrical space, the pictures were taken in close proximity. You can pan and zoom with the pictures to get the necessary breaker information, connected panel schedule, as well as all information and obstructions they may see in this tight space. You'll see the electrical gear is almost up to the structure, making it very difficult, and the mechanical even tighter. Here in a crawl space, all that information was captured and relayed to the contractor, where a 2D representation, even with sections and isometric, sometimes is difficult to understand exactly what the site conditions are. And this visual representation makes that picture very clear to the contractors. So from here, we're going to go to true reality capture. This example is our BLK 360 LiDAR scanner with integrated 360-degree photographs. And this was used to develop a colorized point cloud. Again, the user is immersed in the space, but here with an intelligent model. This has the LiDAR component. Navigation is point to point with the floating orbs, and that allows jumping off points as well as giving an idea of where the perspective of where the scan was taken. Again, spacing, location, planning of those scans is important. But here we have that intelligence. Dimensions are included in this scan. Annotations can be included within this scan. Within the reality capture, we can also alter the display. You'll see the point cloud can be changed from the picture to other perspectives to understand and see elements within that. Further annotation and dimensions are included within this model to help relay that information, make it very clear to the project team, and this was also shared with contractors. This example was a link shared to contractors that was time-based. It expired after bidding. And as Tony mentioned, that can be with or without a time, and it can be shared openly amongst all users. So we go to construction. Now, construction includes kickoff, progress, inspections, punch list closeout, and many other milestones. But we look to apply this technology, again, on a case-by-case basis, but where it's important and necessary to capture progress, or maybe even relevant information of things that need to be addressed. So going to the next slide is this information is a scan that was done above a ceiling cavity. During construction, initial inspection reports noted deficiencies within the components installed above the ceiling. However, as it progressed and when final inspection came, all the ceiling tiles were installed, which makes it very difficult to verify that information. Through the use of LiDAR scan in this case, we're able to see the above ceiling information where little to no light was present. With a LiDAR scanner, light is not needed because it's a laser. And you see we change the perspective and the information to show the colorized plot that helped capture the different structural elements, conduit, J-hook, even ductwork within that cavity to help confirm that the necessary items were addressed. So the LiDAR scan can be used also on floor slabs. Here's a great example where after construction was done, there was a lot of pooling of water on the slab. There were tolerances and sloping, et cetera, that was necessary and clearly defined in contract documents. But it's hard to see exactly where those gaps or where the delineation is with the naked eye, or even getting close up with a level or other technologies. But through LiDAR scan, we can place the scanner and capture that information within millimeter accuracy to clearly denote and clearly call out where corrective action was necessary. So the scan provides great detail, and we can hone in on where quality issues were necessary to address excessive slope that affect ADA, as well as all the pooling that was left over from the final product to get the correct final product for our clients. And it can also be used during construction where existing information may have not have been clear. Here, we're working in Philadelphia, an established city where there's a train center here that had a stair. We're adding an elevator to make it ADA accessible, but all that information was from, structures that were 1800s, very old. So here was ultimately what the vision was, to change that stair as well as build an elevator on the end to make it accessible to all users to help facilitate use of the subway system. Even further, cutting the section to give that stair representation as well as the elevator. And it's important to note, we had to increase that excavation, increase an excavation in an established city with information that may be documented, but is it accurate? So going to the utilities, sorry, I know they're early 1800s, part of the city, but these were 1930s that we had information back to. It shows the stair and all the crossing utilities within that area. Now, surveys can be performed within line of sight. There is some, ground penetrating radar, but some of that information is hard to see and capture until it is opened up. Excavation was done very carefully with vacuum excavation. And here we're going to see these utilities, go back one, sorry, Tony. The utilities straddling that stair. You'll see on top and on bottom all of the items that we had to preserve and maintain, with that elevator also going with additional excavation. So going forward, yes, the excavation was done very carefully with a vacuum. Therefore, we weren't bringing in jackhammers and all the necessary things to not disturb those utilities, but make sure that we removed and excavated in a properly planned process to see that we're not disrupting what's there. So when we come down, this ultimately was the goal, to do the new elevator shaft and still straddle all those utilities that were within that additional excavation. However, when we come to it, these are some of the conditions that we're seeing. Some of the utilities were shifted over, as well as underpinning of the building extended further and even into our excavation. So when it was excavated, we brought in the LiDAR scan. This gave us accurate information within millimeter accuracy of all those pieces that were captured, to clearly denote to the contractor and the project team of what was necessary to facilitate and slightly shift elements to complete the project. So ultimately, the excavation example, as we're seeing here, we were able to still get that same representation, including the elevator, and help streamline the construction activities through the use of LiDAR scanning to get all the relevant information to help the project team stay on schedule and be agile to respond to site conditions that we're seeing. So to summarize, through 360-degree photographs or reality capture, or both, it helps promote good health, increase safety, and improves participant welfare by limiting exposure of large groups of people. This has been applied to help support COVID-19 resiliency and continue the recovery efforts while maintaining business continuity for our clients. They can be used and shared externally, depending on the application, without the need of specialized software. We use Syntu, as Tony mentioned, and that, while we have licenses and capability, but we can share that link out in a read or read-write application to help maintain that continuity and collaboration. And both technologies, 360-degree photographs and reality capture, allow team members to interactively navigate that 360-degree visual twin model to assess the scope of work and increase design accuracy as well as collaboration. So we'll wrap up with that. Obviously, here's just some necessary APA slides, as well as the next slide to stay informed of all APA information that's going forward. So I'll leave you with there. I know there are questions potentially from the chat, and we'll start to look and address those questions.
I'm going to ask the audience that if you have a question for Bill or Tony, to please type it in the chat box, and we'll soon get started with everything. While we're waiting, gentlemen, question I have for you is, did you see a time difference from when you did the face-to-face to going virtually? Did you see that there was, did it take longer to do the virtual versus the face-to-face?
So I would say it actually was quicker. You know, obviously there's not the travel component. There's also, depending what the protocols are, we have some clients where you actually have to take a rapid test before even visiting the site, or do that test on site. So you don't have all those hurdles to take. You know, obviously there is a little bit of processing on our side to make sure that information is clearly shown, processed, shared amongst the team members. But with the picture-in-picture view, it gives a very clear perspective where that information was captured, showing which way you were viewing. And we link that to a floor plan to help keep that connection between what the design included with also what was captured on the site.
Okay, well, thank you. And all right, questions are coming in. Is this a significant cost add to a project, or is it a saving? Not time, but cost.
Well, I'll start there. This is something we're using regularly on projects. I'll say, as far as the 360-degree photo, that's in anyone's survey bag. We bring that out on every project because, again, the cost is reasonable. You know, you're only looking somewhere around $350 to $1,000, and the information's invaluable. As far as a LiDAR scan, we have to make sure that it's planned and that technology is available. But in a lot of cases, if we're trying to get that existing as-built information and develop the backgrounds, it's a huge savings on effort and the lift necessary to, you know, pull tape, develop those backgrounds, and to be honest, you get even a more accurate reflection of that information with the LiDAR scanning. So all in all, we see it as, obviously, it's an investment that, you know, the company has taken, and it is an investment that, you know, we look to recoup over time, but we don't push that directly on the clients. It's something that has been invaluable to, you know, ourselves, as well as a lot of our things that our clients are asking for to maintain that business, because COVID restrictions have been all over the place, you know, as time's gone. Been very restrictive. Things have opened up. Things have gotten restrictive again. And this information exchange has been very helpful.
Yeah, and I guess you could also add, you know, it really depends on what involvement and what investment you want to actually make with reality capture and, you know, what you're doing with it. Obviously, if you were to take the step to buy a LiDAR scanner or buy a drone with a camera or a LiDAR scanner, you're going to have that initial cost. You're going to have a cost if you start to capture large amounts of data. The LiDAR point cloud models that you're developing are not small in size. They could range couple gigabytes, they could go upwards of hundreds and hundreds of gigabytes in size. So depending on how much you're capturing and how much you're going to start to store, you're going to have that cost on the back end if you get set up with servers or you get set up with a cloud storage solution to start maintaining your data. But like Bill said, we don't pass that cost off to the clients. We are utilizing it because it's so beneficial to our design, and it's really become a norm for the AEC industry as well as the survey industry, where you could pay a licensed survey firm to go out and capture your scope of work with LiDAR 360 cameras or drones or all of the above.
Okay, thank you. Well, we had a second question come in, but it duplicates the first question. So if we don't have any other questions, I'm going to thank Bill and Tony for your time today for this very informative webinar. And as always, to our attendees, thank you so much for taking time to be with us today. We know it's not easy out there, and we appreciate you taking the time. So until next time, be safe, stay healthy, and be kind to one another. Thank you so much for joining us today.
Thank you very much.
Bye.
Bye now.